Hi, the lecture today is the fundamental of sampling. The sampling of continuous signal at periodic intervals has become a very important and practical mathematical operation. One of the main concerns when signals are sampled is the accuracy with which the sample signal is represented by its sample values. Also, what type must the signal be and what must the sampling interval be in order that an optimum recovery of the original signal can be accomplished from the sample values? This is the question that we need to answer. So the major question here is what is the sampling frequency should be so we'll be able to reconstruct the signal that we are sampling. We have here on this slide to the left the continuous time signal x of t, and we need to sample the signal to obtain the discrete time signal x s of n. So we'll get that from that. So what is the sampling interval? Or what is the sampling frequency? So we can do this job in the right way. Well, I will just give you a simple example here. We have a straight line. And this straight line has an equation. You can figure it out if you look at the diagram, but it's not an issue. And we want to sample at every t of s this continuous straight line. So you will find value here and value at -2 and -1 and 0 and so on. So actually you can get this one by multiplying the signal of that we have here, the straight line. Okay, if you can multiply it by train of pulses, these are pulses and they are separated by period equal t of s, uniform sampling. And this is like, delta. So this is delta t at t equals 0. And that's delta t minus ts. And this one, it's delta t minus 2ts, and so on. If you go here to the left, that will be delta t plus ts. You move ts every time. One time to the right, one time to the left, t, 2ts, and so on. So if you multiply this train of pulses by this signal, the continuous time signal, then you will get the discrete one here. And you will find each element, like if you multiply delta t by the value here, you will get the value of the function at t equals 0, which is x of 0. That's the height. And you multiply it by delta t, then the value is equal x0 delta t, because delta t has a position at t equals 0. Let's take another one. If you multiply this pulse by the straight line, then you get the value here. But this value is equal x of t equal to t of s, which is equal 1 in this case. So you know the value here, but you want to locate it here. You don't want to locate here in this same value. You can put it there, here. How can you keep it at the same place? You attach next to it delta t minus ts. So when you do that, it means the position of this value, it's shifted by ts to the right here. So that's ts. So that's how can you represent discrete time signal after you sample the continuous time signal. And simply we can say it's the product of the signal itself times the train of pulses, which we are going to call it here p of t. All right. Now, since we represent it as a multiplication, this is a multiplication, that is the signal x of t, it's coming here, and that's the pulses p of t. We just explain it and then multiply, and then you get the signal here. All right. Well, this signal will say it's band limited signal. What does it mean? It means if you do the Fourier transform on this signal to find the spectrum of this signal, you will find it's limited by the upper frequency omega max. Does not exceed. After omega max, you will not find other frequencies You'll not find other component with frequencies higher than that frequency. So it's limited. It's not, maybe, okay, maybe I'll give you another example. One is not limited. It's like that, you know. So, I mean, like, this is, I mean, the omega. So it's like, I mean, you can find component at every frequency. But in this diagram, we are working only with band limited signal. It means you have a spectrum in this range of frequencies, nothing beyond this frequency limit. So we call it band limited signal. Well, what's the objective now? The objective, we need to find the best f of s, or reasonable switching frequency that will allow us to sample the circuit in a way that we can reconstruct it back. Great. Well, let's just go to the math of it. Now, that's the expression. X of t, the continuous time signal, and b of t, the train of pulses that we have it here. And this is the continuous. And x s of t, that is the sequence or the discrete version of this one. So we need to find Fourier transform of this one. To find the Fourier transform for this one, first we have to make some mathematical operation on P of t. B of t, as you know, it's a train of pulses, and it's far from each other by ts. So it's repeated every ts. So it's a periodic signal, and the period is equal t of s, or ts. So we can use Fourier series to expand this or express this signal or this train of pulses into a series of Fourier series terms. All right. So we are going to use exponential. You might want to use trigonometric. That's okay. You get the same result. So that's the formula for Fourier series. Ck is the coefficient of Fourier series, and then multiplied by e power jk omega st, whereas omega s is the switching frequency, and you can calculate it. You say omega s is equal 2 pi divided by t of s, switching period. Right. Now, how you find Ck? Ck, you find it by the same expression that you learned before in this class. So Ck is over 1 over Ts, the integration of delta T times e power minus jk omega st. Well, when you integrate, when you integrate any function multiplied by delta T, that's a property that you learned before. Let me just remind you, if you are going to integrate delta t by any function with respect to delta t, is going to be equal this function at t equals 0. All right. So that's what we have. Delta t time, this is your function now. So just it will be equal this function at t equals 0. When you put t equals 0, e power 0 is equal 1. So this one be equal 1. The whole thing equal 1, and you multiply by 1 over ts. That's 1 over ts. So the coefficient of Fourier series of the train of pulses b of t is equal 1 over ts. Substitute here, and you can get it outside the sigma. So it's 1 over ts sigma e power jk omega st. What is that? That's pt. That's another way to express pt in Fourier series. It's equivalent to this one. All right, great. Next, modify the expression. Just you got pt, put it there in expression and find xs of t. So I did that, just I multiply it, and I put xt inside here. So that's, the expression inside, the sum 1 over ts. I put it outside. Right. Next, we are going to find Fourier transform for the expression we just got recently. All right. How you do that? To find Fourier series of a function, I will remind you about the formula. It's the integration from minus infinity to infinity. F of t, the function of time, multiplied by e minus j omega t. That's it. And the integrate with respect to delta t. Now your function is xs of t. All right. So that's xs of t. X of t, the whole thing here, you put it there in the integration. And just we are going to switch the integration outside, inside, and the summation outside. It's the same, doesn't affect it. So we'll just focus on that one. Well, how you got this one? Just let's make it easy, step by step. When you multiply, that's x of s, you multiply by e minus j omega t. You know that xs, let me just take one term here. It's equal x of t e to the power j k omega s t. All right. And then multiplied by e minus j omega t. So you'll take minus j as a common factor and t, and then see what's happening here. You have omega, and you got minus k omega s because you have minus outside here. So that's how we got these things here. When you look at this expression by itself, this is the formula like just I wrote here. The only difference that omega is subtracted by minus something. What does it mean? Well, if you know that it's the f of omega is equal to the integration of f of t exponential minus j omega t, what about if this omega is something else? Like alpha, you will have but alpha. If you have omega dash, you have omega dash. Whatever you have here, you put it there. So if you put there, instead of omega, you put omega minus k omega s. And this is what you have here. So you replace this by omega minus k omega s. That's what you do. So now you do not have x of omega. No, you have x of omega because it's x of t. If you don't have this one, you will have the same thing, x of omega. But because you have this now, the new one, so you replace omega by omega minus k omega s. So that's the Fourier transform of the discrete time signal after sampling. Very important. Let's look at this summation. I will just get some terms. I will substitute by k, not all the values, of course. Remember, what is that expression? That's x s omega. Let's just change the color to make it clear because it's really important. So just make it darker a little bit. All right. So x s discrete omega is equal. Many terms. Let me take the one when k equal minus 1. So x omega minus k minus 1 minus positive plus omega s plus both k equal 0 x omega plus both k equal 1 x omega minus omega s. And then you continue. I want to get just few terms like that. What's x omega? This is the original spectrum of the continuous signal. Let me show you. I will remind you. That's it. That's x omega. Just let's clean it. That's x omega. It's a spectrum or Fourier series of xt. So that's how we got this one. Fourier transform. All right. So it starts from minus omega max to plus omega max. This is given, or you can get it from this graph. Well, so that's x omega. And you observe when I show you, it's in the center, like this is x omega. It starts from minus omega max up to plus omega max. All right. What about this signal? Well, if this one center at 0, because you substitute what's inside the bracket, omega equals 0, find at 0 the center. If you put omega plus omega s equal to 0, so omega is equal minus omega s, so the center of this one minus omega s, it will be the left of 0. And then you sketch the same thing. Because it's the same thing, just shifted. It's x omega plus omega. It's the same shape, the same size, but shifted. All right. So since shifted this minus omega s, you will measure omega max to the right and the left. Let's look at this one. Omega minus omega s equals 0, so omega is equal omega s. So the center at omega s, and then you sketch the same spectrum with the same bandwidth, which is omega max and omega max. So that will be omega s, that's omega s plus omega max. And this one will be omega x s minus omega max. So, and you put them all in one graph. Let me show you the result here. That's what I put them together. All right. That's the spectrum. What I plot here, the spectrum for the discrete. I hear somebody asking, only we have 3 things. No. You have to infinity. But I don't have space. You can continue to minus infinity plus infinity. So what do you observe? The first observation is that's the original spectrum of the continuous signal that I started. Then after sampling this signal, we got many copies. The same copies, just repeated. That's the first observation. All right. What's the second thing? Well, You remember we said that the center, this is x omega minus omega s. So the center at omega s. And we know that the bandwidth, that's omega max, and that's omega max. So if this is omega s, it may be somebody asking, you measure from 0, of course, this is all omega s. And then you go back omega max, so you got this point, omega s minus omega max. And then when you go ahead, forward, then you add to omega s this omega max, so be omega max plus omega s. Well, let's just, see what's happening here. You observe no overlapping. It means this is a spectrum, and this is a spectrum, and there is a space here, nothing in there. All right. What does it mean? There is no overlap. Is it good or bad? It's good. Why? Because, if you don't have overlap, so every spectrum will be independent of the other spectrum, so no overlapping. You will not mess up the spectrums. You will not create any other frequencies except what you have in your signal. Let me give you a sample. So if you don't want to have overlap, this value, what is this value? That's omega s minus omega max, right? That's omega s, and you go backward, you subtract omega max, because this is omega max, omega max. All right. The overlap will not happen if this value bigger than this value. What is this value? Omega max. It means omega s is greater than, you move this one to be omega max plus omega max will be omega s is greater than 2 omega max. What does it mean? It means that the switching frequency, if it's greater than double the maximum frequency component in the signal that you want to sample, you will have no overlapping. You will keep the signal as it is. You will be able to reconstruct it. So it's good. So this condition is important. Very important. All right. Let me give you just a numerical example. Let's say that the maximum frequency here in the original signal was 5. So that would be minus 5. Now, let's say that omega s is 15. It means you're making switching equal to 15. So let's say if you are doing the right thing. Well, if this is 15 and you know the omega max equal 5, so if you go backward by 5, you got 10. So when you have 10, this is 5, so it's much, bigger than 5. So there is no overlap. That's true. So when you have omega s more than the double of omega max, you don't have overlap, and you can regain and reconstruct the signal back. What about if you do not do that? Let's say that your omega max is still 5, and that's minus 5, but you didn't make switching frequency satisfying this condition. Let's say that you make it equal to 8. If you go back 8 minus 5, you get 3. So 3 is smaller than 5. Obviously, there is overlap here. And if I continue to sketch everything, you will find overlap. What does it mean, overlap? It means here there are some signal with different frequencies are mixed. If you reconstruct back the signal, you will not get the same thing. And that's the problem of overlapping or aliasing. So that's really important. So this condition is violated because obviously that omega s here, which is 8, less than the double the frequency, because we say this is 5, it means 10. So it will not regain back the shape of the signal. And that's an important theorem about it. Call it Nequest sampling theorem, or sometimes you call it Shannon. So it said that a band limited continuous time signal, and I'll explain that, means that it's limited by the frequency maximum, doesn't go ever to infinity, can be sampled and perfectly reconstructed from its samples if, you can sample it and then you go back again. If what? If it's sampled over twice as fast as its highest frequency component. So you look for the signal that you want to sample, and first you do the Fourier and check the components. You'll find it has many components. You see the highest frequency component and check the value of its frequency. And you see that said, let's say you found that the maximum frequency in this component is equal to 30 hertz. Said, okay, my switching should not be less than 60. Should be higher than 60. That's what Nequest said. So you can accurately represent. All right. That's all. I hope that you got it. Thank you.